Welcome to Study Loop.
Okay, so in this problem, we have one solenoid wrapped around another, and we're given a lot of information. So let's just start off by recording in variable form all of the different information that's given to us. So these are the number of turns in each of the coils. Here's the length of the first coil. We also know its diameter. And I'm converting everything to SI units so that our lives will be easier down the line. Here's the current that's going through the first coil. And then lastly, we also know how quickly that current is changing. And that seems kind of big, so let me just double check to make sure that's right. Yep, that's what the current is, and that's how fast it's changing. 1.75 times 10 to the 3 amperes per second. And so in part A, they are asking for what that magnetic flux in the first coil is. And so because we have tightly wound coils, the magnetic flux through both of them is going to be the same. And it's easier to solve for the second one. So that's what we're going to go ahead and do. And that's going to be the product of the area and the magnetic field. And so we can further simplify those by noting that the magnetic field is given by mu naught N1 I1, and then the area is given by pi r squared, but we're not given the radius. We're going to have to do diameter squared divided by 4 instead. We can further make one more substitution because we actually aren't given the number of turns per unit length, but we are given the number of turns and the length, so that's what we're going to plug in instead. And then over here we have pi d1 squared over 4. So now we can go ahead and plug in numbers. Let's actually do that up here. This is going to be monstrously long. So we plug in the SI value of mu naught, which is 4 pi times 10 to the minus 7. The number of turns is 300. We have a current of 0.12 pi and a diameter of 0.0200 squared, all divided by 4 times the length, which is 0.250. Okay, plug that into a calculator, and then you will get that the magnetic flux, which is measured in units of Webers, is 5.68 times 10 to the minus 8 Webers. Cool. Okay, so that was part A. So now we can do part B over here. And this is asking for the mutual inductance. So we can find that from this equation involving the number of turns and the magnetic field. Just to be super explicit, remember we said earlier that because we have tightly wound coils, the magnetic flux through each of them is going to be equivalent. And so we just plug in numbers. Let's do that down here. So we have 25 turns, and then recycle our answer from the previous part. divide by that current in order to get a mutual inductance measured in henries of 1.18 times 10 to the minus fifth henries. Good. And then wrap things up with part C is asking for the induced nth in the second coil. And so we just use this formula. In order to find that, recycle our answer from the second part. And finally make use of that changing current. Plug that into a calculator and then you get an induced nth of this. And we're done.